unsteady state heat transfer without lump capacitance assumption. For 1D, I'm sorry, 1 dimensions. 1-dimensional, let's say. In position. Let's actually start with the case where we have, what was the geometry that we studied? I guess we studied the sphere, right? For the time being, let's make this problem simpler and let's work with the slab geometry. Let us work with slab geometry to make things simpler. Things less difficult, let me say, less difficult. Okay. And I'm sorry, our system is going to look like this. We have a slab, infinite in 2 dimensions, so it's also like going in this direction as well. Okay, but I'm interested in 1 dimension, so I'm only interested in the changes along the x direction. Okay, and I'm actually heating this or cooling this slab with some fluid, H, Tf. Tf is the temperature of the fluid, H is the heat transfer coefficient of the fluid. Now, I'm going to assume that the temperature actually might change within the slab, right? I can have something like this. Or if it's cooling, it's going to be something like this. Right? It's going to cool with time. But there's going to be also like a step down from the surface of the solid and the fluid temperature, which actually make things more difficult. So we can make things simpler by still assuming the temperature varying within the slab, but not at the contact. So imagine that the temperature deviation from the solid surface to the fluid is so small that you can neglect it. So imagine that like 2 cases. You can have something like this, right? Which actually you cannot assume that the T surface is equal to Tf, but you can also have a counterexample where you have something like this, okay? And I would like to investigate the purple case. I would like to investigate where the surface heat transfer resistance is negligible, so that I can make an assumption that the fluid temperature is the same as the surface solid temperature, okay? And it is when, if you do the same analysis as we did in the previous class, this corresponds to the case where the bio number is very, very large. On the other hand, this case, where you have almost like comparable deviations in the temperature, this corresponds to bio number is almost equal to 1. But this corresponds to bio number is much, much larger than 1. Okay. So let me write down all these cases and just to make things clear. So, okay. Imagine you have the slab, 1 case where you have this. Okay. This is bio number is comparable with 1. This is bio number much, much larger than 1. And as you learned in the previous class, this one corresponds to bio number is much, much less than 1. Okay, so these are the summary of the previous class. In this class, let's pick bio number is much, much larger than 1 case. Okay, and let's make it in a bubble, and let's apply it for our situation. Okay, so we are going to assume, so let me write it here. In other words, assume negligible heat transfer resistance. Okay, and okay. When you assume the negligible heat transfer resistance, this means T surface at any time almost equal to the fluid temperature. Okay? Assuming bio number is much, much larger than 1. Good. So we set the stage. This is our problem, and we want to find out the temperature distribution within the slab. Okay. And how are we going to do it? Let's do shell balance. And the shell I'm going to pick is going to be, for symmetry reasons, is this thin. You can actually, it actually extends in this direction as well, but you can assume the W and B, or whatever you want to call it, W and H maybe. They're very large. You can basically call the area of this rectangle A. So as we're going to see, it's just going to disappear from the equation. We're going to think about whatever comes in and whatever goes out. This is Q at X, Qx at X, Qx at X plus delta X. Okay, so let's do shell balance. Let us conduct shell balance. Okay, in minus out plus generation is equal to accumulation. Let's say it's not steady state, so I have the accumulation there. Okay, and let's imagine there is no generation. Okay, assume no heat generation or thermal generation. Thermal energy generation. What's coming in? It's Qx times area gives me the rate of heat in, estimated at X. It's this thing. Minus whatever coming out, Qx A at X plus delta X is equal to accumulation, which is the rate of change of thermal energy, d over dt. We're going to use the MCP delta T, right? The energy, thermal energy is MCP delta T with respect to our reference. So the mass of the slab is the density of the material times the volume of the material, volume of the slab, I mean, and the volume of the slab is nothing but the area times the delta X. That's the volume of the slab. Okay. It's the volume of the slab times temperature of the slab, T at X. T at X and T. Okay. let's assume the rho constant A is constant, so you can divide both sides by A and they're going to cancel, right? Constant throughout. Okay. If it were a spherical geometry, it would not be canceling. You would actually have like R terms within the derivatives. And let's divide all sides by delta x.
Do you also need to have CP on the right-hand side of the equation?
Exactly, yeah. How did I forget about it? Yep, exactly. MCP delta T, exactly. Thank you. CP T. There you go. Okay, excellent. Let's divide both sides by delta x. And keeping in mind that the delta x is not a function of time, my shell is not shrinking or expanding with time. You can also take, like, you can also do shell balances in such a way that the delta x changes with time, but this is not a case where we have like an expanding solid or displacing solid. So I'm good to actually take the delta x not changing with time. So you can actually cancel the delta x's. And you can take the rho out, the CP out as well. And on the left-hand side, you're going to have the minus positional derivative, but it's going to be partial derivative of Qx is equal to rho Cp d temperature, or del temperature, I'm sorry, over del T. Because I have two independent variables, time and position, I'm doing partial derivatives. So far, so good. And let's plug in the Fourier's law. From Fourier's law, Qx is equal to minus k del T over del x. And I don't need to write the flux along the y or z directions, because I know that there are no fluxes along those directions, because my system is infinitely along the y and z directions, so there are no end effects. So I can neglect the end effects. So I can assume that neither the temperature is changing nor the flux is non-zero along the y or z directions. So let's plug this in, and you get minus minus makes plus, k is constant, k times del squared t over del x squared is equal to rho Cp del T over del T. And there was a variable called k over rho Cp, right? K over rho Cp. What was the name of this variable? We called it alpha, right? What was that? We learned it in lumped capacitance method, I guess, right?
Was it thermal conductivity?
K is the thermal conductivity. Alpha is the thermal diffusivity, as we learned before. And it has the units. If you actually do the units, like dimensional analysis, you're going to see that it has the units of meter per second square. And that's the reason why we call it diffusivity. We're going to learn later that mass diffusivity also has the same units, meter per second square. And probably in fluid mechanics course, you have seen that the momentum diffusivity also has the units of meters per second square. Okay, so basically, instead of using K, we use alpha to be able to actually make some analogy between mass transfer, heat transfer, and momentum transfer. For the heat transfer, we call it alpha. For the momentum transfer, we actually use nu. Just a reminder, nu was momentum diffusivity. and it had also the units of meters per second square. DAB was the mass diffusivity we're going to learn later. So this is the reason why we called all the same diffusivity, because they all have same units and it corresponds to how fast the transport happening. Okay, we'll learn later, let's say, as we will learn later. Okay, but we learned the part that it corresponds to how fast the transport is happening from the previous class, right? So with the simplification, I can just have k over rho Cp on the left-hand side, so I can call it alpha del squared T over del X squared is equal to del T over del T. Okay. And the units make sense. You can see that this has the units of meters per second square. This has meter squared. I'm sorry, I made a mistake here. Meter square per second, I guess. That's okay. So this is meters squared per second. Meters squared per second. Sorry for the mistake. Okay. Yeah, the diffusivity has the units of meters squared per second. And you can see that these units make sense. Okay, you can check it. Okay, and you can also write it as taking the alpha to the other side. Del squared T over del X squared is equal to 1 over alpha del T over del T. And let's box it. This is our differential equation, partial differential equation, second order partial differential equation. Let's write down our initial conditions as well. Initial and boundary conditions. I have two boundary conditions and one initial conditions. Initial conditions means what is the situation of this slab at time is equal to 0. At time is equal to 0. Let's take the entire slab at the same temperature. Okay. T is equal to T0. Imagine that you have a slab at, for example, 400 Kelvin. You put it in a cold fluid at 300 Kelvin, and you just watch it cool down. And let's just take the entire slab to be at the same temperature at time is equal to 0, but it's not going to be at the same temperature while it cools down. You're going to have some temperature deviations within the slab. It's only when time is equal to 0, it's homogeneous. Boundary condition 1 is one end of the slab, here, this one. The temperature is at Ts, so at X is equal to 0. Let's say the temperature is equal to Ts. And that's equal to Tf. Okay, so you can actually have it or not. Depends on which quantity you want to use. As long as they are equal, that's okay. Boundary condition to the other surface of the slab at X is equal to L. Temperature is again Ts, and that's equal to Tf. Okay. Now, what are we going to do? We're going to solve this differential equation, but I don't want to solve it for, I don't want to solve it when it has dimensions on it, and I want to non-dimensionalize this equation. I would like to non-dimensionalize this equation. Okay. Why? Why do you think we should non-dimensionalize this equation? Any idea?
Because it's easier to solve.
It's what?
Easier to solve.
It's easier to solve. Maybe it might be easier to solve. Yeah. One reason might be that. Another reason is I want to non-dimensionalize it to simplify the boundary conditions, boundary and initial conditions, so that instead of like I have my dependent variable equal to t0, it's going to be equal to something like 1 or 0. Okay, so I'm going to simplify the initial and boundary conditions. Well, that's one thing. The other thing is, if you non-dimensionalize, you can actually solve the problem in a general setting where you can actually come up with the solution, and you can say that, okay, so this is the solution, and you can even tabulate it. For example, imagine that I'm tabulating this result for, imagine that I solve this equation, and I know the value for t as a function of time and position, okay? And I want to tabulate it or plot it. But if I tabulate or plot it, it's not going to be a useful information, because in the table, I'm going to use something like seconds for the time, or maybe like meters for the position, right? But maybe later, some other people is going to use this for a nano slab geometry, and he or she will need to resolve this equation and try to find out the solution for the micrometers or nanoseconds or whatever. So we're going to make it independent of the units. Okay. First, simplify EC and IC. Second reason is the resulting equation or the solution will be more generally applicable. And more importantly, thirdly, non-dimensionalization might give you, in some cases, some physical insights. Gives us physical insights about the problem. Because, for example, the reason why this has units is because, you know, the t has units, x has units, alpha has units, and so on. And the reason why your plots like t versus x are going to have units Kelvin and meter, whatever, is because you have an alpha, a unit, like a quantity which has units in your equation. And depending on the value of the alpha, you can come up with different plots. And if you plot it for copper, for example, you're going to have a completely different t versus x t. If you plot it for aluminum, you're going to have a different T versus XT, because alpha for the aluminum is different than the alpha for the copper. But if you non-dimensionalize, you can see something emerging in the equation, which is going to be unitless. And for the copper and for the aluminum, you get the same equation, and you can have an idea about why these two systems behave the same, and you can come up with some non-dimensional numbers that tells you about how the system is behaving more generally. So it's beyond any particular problem like copper or aluminum. So you're going to get an equation which is going to be more generally applicable, and it's going to give you an insight, because it's going to tell you what is the important non-dimensional number or dimensionless number for this type of problems. Okay? Okay, those are the reasons. So let's open another page to solve this. Page 2. Non-dimensionalization. Of non-dimensionalization of del square t over del x squared is equal to 1 over alpha del t over del t with the boundary conditions and initial conditions. This is equal to 0, t is equal to t surface, condition 2, at x is equal to L, t is equal to ts again. Okay, so let's come up with a dimensionless temperature. Okay. Theta is equal to any suggestion on writing a dimensionless temperature? So what are the characteristic temperatures of this problem? What are any temperatures given in the problem, so that I can make use of them and non-dimensionalize the temperature at any point? Any idea? Come on, you should be able to do this in the tests or in homeworks.
TS and T?
TS and what?
And T, just normal T?
Yeah, T is any temperature. It's not a characteristic temperature. Do you have another candidate for a characteristic temperature? Or is it just
TF?
T what?
TF?
TF, you said?
F.
A T naught?
No, TF. Oh yeah, T naught. Yeah, T naught.
T naught. Okay, T0. Okay. Yeah, we have TS and T0, the initial temperature and the surface temperature. So I can make use of the two, and I can either say T minus T0 divided by TS minus T0, or T minus TS divided by T0 minus TS. Okay? Good. Okay. Good. So let's take it theta is equal to T minus TS divided by T0 minus TS. Okay. And dimensionless position. Psi is equal to, let's divide the position by a number which has the units of position. Is there a characteristic length for this problem?
X over L.
L, x over L, exactly. So we're going to use these two. And after doing this correctly, you will find that del squared theta over del psi squared can be written in terms of del t over del t, and you get L squared over T0 minus Ts, del squared T over del x squared. Do this as an exercise. You know how to do it, we learn it, so I don't need to, I think there's no need to go over this again. Okay. And del theta over del t, unfortunately I'm not able to non-dimensionalize the time for the time being, but it's gonna appear soon, don't worry. It's gonna be apparently clear how we can 1 over T0 minus Ts del T over del T. So let's instead of this in this equation, let's plug in this, this times the reciprocal of this. Okay, good. So our equation becomes T0 minus Ts divided by L squared del squared theta over del psi squared is equal to 1 over alpha times T0 minus Ts del theta over del T. Okay, and let's do some simplifications. And the only thing that's not non-dimensionalized in this equation is the time t. So let me collect everything with, like, combine everything non-dimensional with the t, so that I make sure that I actually get a non-dimensional quantity there too. So my equation del squared theta over del psi squared is equal to del theta over del, in parentheses something. I'm going to dump everything with the t, and it looks like it's alpha over L squared times t. Okay. Or I can write it as t over something, so that it looks non-dimensionalized, t over L squared over alpha. Okay. Good. And let's say, let us define this term in the denominator as the characteristic time, because when you divide it by, when you divide time by that, you get a non-dimensional number. So apparently L squared over alpha should have the units of time. So the tau is equal to L squared over alpha. Let's define it as characteristic time. Okay. And so our equation becomes del squared theta over del psi squared is equal to del theta over del. Instead of t, like t over tau, let's call it dimensionless time. Let's call it t tilde. Okay, and our equation becomes del t tilde. Now, I have accomplished to have an equation with all the terms non-dimensional. Okay. Okay, good. And one thing about this equation, let's write down the boundary condition and initial conditions, and let's celebrate this equation with a couple of observations. So the initial condition at time is equal to 0 is equal to t is equal to t0 becomes, at t tilde is equal to 0, the theta becomes equal to t0 minus ts divided by t0 minus ts, which is 1. As promised, we get a simple theta number for the initial condition. Boundary condition 1, at x is equal to 0, which means the psi is equal to 0. The t is equal to ts, which means theta is equal to ts minus ts divided by something, which is 0. So the theta is 0. Similarly, for the boundary condition 2, at psi is equal to L over L, which is 1. Theta is equal to 0. There you go. Now let's celebrate this equation. When I solve this equation, I'm pretty sure that I solved this for copper, for aluminum, for plastic, for all the materials. I have only one equation. So I will have only one solution for all the materials. Okay. What does it mean? They're all going to behave the same, but maybe their characteristic times are going to be different. For example, the L square over alpha for a material for which the alpha is very large, like the thermal diffusivity is very large, for example, copper instead of plastic, then the characteristic time is going to be large. So you can use the same equation, but this tells you that it's going to take longer time for the plastic to get to the same temperature profile. But it tells us that it gets to the same temperature profile no matter how long time it takes. But for the copper, it might take 1 second. For the plastic, it might take 10 seconds. So that's something amazing, I guess, because it's not like they have different temperature profiles. They evolve similarly, but one evolves faster, the other evolves slower, just because their characteristic times are actually different for the different systems. Okay, that's the lesson actually that we actually learned from this non-dimensionalization. Cool. Let's solve using which technique should we solve? I think we had an equation like partial differential equation, right? When we learned about two-dimensional heat conduction. And we used the technique of, what was the name of the technique? I want to apply the same thing here. Come on.
The separation of variables.
Excellent, yes. So we're going to do the separation of variables. Let's do it here. Variables will be used to solve. Okay, so we're going to assume the theta is equal to a function of psi, position, times a function of t tilde. Okay, and from here our equation becomes the del square theta over del psi square becomes f prime prime psi, because you take the second derivative of theta with respect to psi, and it's only this term which actually depends on the psi, so you take the second derivative of the f. And it's going to be an ordinary derivative because the f is only a function of psi, but not a function of t, times g t tilde is equal to, on the right-hand side, I have del theta over del t tilde, which is f psi times, this time, the derivative of the g, but the first derivative, not the second derivative, t tilde. We're going to actually do the same trick. We're going to divide by fg to make one side only f's, the other side only g's, one side only function of psi, the other side only function of t tilde. So let's divide both sides by f psi gt tilde f psi gt tilde. And you get rid of these two, and you get rid of these two, and you have f prime prime divided by f is equal to g prime t tilde over g t tilde. So, as we said before, this is only a function of psi. But this one is only a function of t tilde. So this must be a constant. Okay. But is that going to be a positive constant or a negative constant? Let's see. Let's check the positivity first. Let's check whether it's a positive lambda square. Okay. What you would get is basically a contradiction, because if constant were positive, you would get a contradiction as below. So you would get g prime t tilde is equal to lambda square gt tilde. From here, gt tilde would be equal to exponential lambda square t tilde, right? And some constant c1. Right? And this would tell you the following. As t increases, to infinity, right? What happens to t tilde? It either increases to infinity or decreases to negative infinity, which is not physical, would not be physical, right? So I would expect gt to be a bounded function. Okay, so that's a contradiction. So this must be negative. Must be negative. So we should have negative lambda square here, and this is the explanation. Okay. Now, so the constant is negative, so I'm going to equate them to negative lambda squared. Okay.